In this video, I'm gonna be talking about biomedical event extraction, and we use hierarchical knowledge graph to have a better event extraction. So I'm gonna be focusing on this paper in 2020. Biomedical event extraction is critical in understanding biomolecular interactions described in scientific corpus. But one of the main challenges is to identify nested structured events that are associated with non-indicative trigger words. We propose to incorporate domain knowledge. In biomedical domain, we use UMLS as a very good ontology, and to better recognize the trigger words, each sentence is first grounded to a sentence graph based on a jointly modeled hierarchical knowledge graph from UMLS. A typical event extraction system finds triggers that most clearly demonstrate the presence of events, recognizes the protein participants, the arguments, and associates the arguments with the corresponding event triggers. But this is an example of UMLS-based hierarchical knowledge graph assisting event extraction. These circles that you see here, for example, this one, these circles represent concept nodes. And these triangles represent semantic nodes. Nodes associated with tokens in the example sentences are bold-faced. Bidirectional edges imply hierarchical relation between concept and semantic nodes. The word induces is a trigger of a positive regulation event. Whose trigger role and corresponding argument role cannot be easily determined with only textual input. The knowledge graph provides clues for identifying this trigger and its corresponding arguments given the red and blue double-line reasoning path connecting the nodes. So we can infer that induces is an action of biological function. A biological function can be quantified as a positive regulation. A positive regulation can result in phosphorylation. Our first contribution is a novel representation of knowledge as hierarchical knowledge graphs containing both conceptual and semantic reasoning paths that enable better trigger and word identification based on UMLS. So that figure showed that a positive regulation event can be better identified with knowledge graphs and factual relational reasoning. Our second contribution is a new graph neural network, graph edge condition attention networks, that encodes complex domain knowledge by integrating edge information into attention mechanism. This one has greater capabilities in reasoning the plausibility of different event structure through factual relational path in knowledge graphs. So you see that contextualized embeddings for each token are generated by Cybert. To know knowledge sources discussed in section are jointly modeled as a hierarchical graph for each sentence, which we refer to as sentence graph. The first step is to make each sentence in the corpus to UMLS biomedical concepts with MetaMap, an entity mapping tool for UMLS concepts. There are 7,000 concepts, and So the next step is concept network construction, where we create a minimum spanning tree that connects everything, because this is our reasoning path. This step is NP complete, so we adopt a two approximate solution that constructs a global minimum spanning tree. The majority of existing graph neural network consider only hidden state of nodes and adjacency matrix without modeling edge information. But we use edge condition attention network to integrate those edge features. Consider them as attention. And so this is how convolution operation depends on edge type, and this one is able to determine the relative importance of neighboring nodes with attention mechanism. So we build it on top of Cybert to incorporate domain knowledge to rich contextualized representations. We take the contextual embedding produced by Cybert as input and produce knowledge-aware embeddings as output. To initialize the embeddings for a sentence graph, for a mapped token, we projected Cybert contextual embedding to initialize its corresponding node embeddings. Other nodes and edges are initialized by pre-trained knowledge graph embedding. So we just use Cybert for the initial embedding of this GNN. To accommodate multiple relation between two entities in UMLS, edge embeddings are initialized by summing the embedding of each relation between nodes I and j. Then we apply layers to encode the graph. The knowledge-aware representation is obtained by aggregating Cybert representations and knowledge graph representations. The entire framework is trained with a multitask learning pipeline consisting of trigger classification and argument classification. Trigger classification predicts the trigger type, the predicted score of each token is computed. In the argument classification stage, each possible pair of gold trigger and gold entity is gathered and labeled with corresponding argument row. The argument scores between ith token and jth token are this. And then we use the cross entropy loss for both tasks. So we have two losses, trigger loss and the argument loss. And we do experiments on Genia. This is good for biomedical domain if you want to do event extraction. And you see that even if you use this model, which is a combination of Cybert and GenaNet, then our F1 score is too low. It is still too low. So even in 2023, 2024, the state of the art is around 68. So it's less than 70%. So there is room for improvement, and it's a good motivation to work on this data set because it's still room to progress. To pre-train knowledge graph embedding, we leverage this trans E that I've explained this in one of the videos in, I think, knowledge graph playlist. So here t denotes the distance between x and x prime, and h and t are just the head and tail. So this is head and this is tail, head and tail. and there are different distance between x and x prime. The dropout is 0.2, which is not too big.